Okay, greetings students. Welcome to the module MOM3602, Theory of Machines 3 at the University of South Africa. In this video, I will give a very quick overview of how to develop the kinematic equations and then relate the kinematic equations to the kinetic equations, basically the dynamic equations, and then we will explain how to use this to develop the equations of motion. So consider a problem as shown below. We've got a rod which is of a certain length. Let's just call it L3. We have the rod which is pivoting at a point somewhere in the middle of the rod by an angle theta. And then connected to the rod, on one side we have a spring of spring constant K, and on the other side we have a damper of damping constant C. And the distance from the end point at which the spring is connected to the pivot point is L1, and the distance from the point where the damper is to where the rod is pivoting is L2, and the total length of the rod is L3 for the sake of argument. Okay. How do we develop the equation of motion for the system? The short answer is we'll apply Newton's second law. What is Newton's second law? Okay, Newton's second law is basically the equation that the resultant force is mass times acceleration, which is mass times the double derivative of the displacement. So the resultant force in the x direction. Similarly, the resultant force in the y direction is the mass times the acceleration in the y direction, which is equal to the mass times the acceleration in the y direction. And then we also have an angular expression Okay, these are the equations of motion using Newton's law, as we can see over there. What does that mean? That means if we have a point that is moving in the x direction, its equation of motion, the resultant force in the x direction is the mass times the acceleration in the x direction, which is defined in terms of this equation. Basically, acceleration is double derivative. Likewise, we have the resultant force in the y direction is mass times acceleration in the y direction, and likewise the rotational form of Newton's second law is the resultant torque resultant is equal to the moment of inertia times alpha, which is the angular acceleration, which is basically the resultant moment of inertia times the angular acceleration. Coming back to our problem, this is the problem. Okay, how do we actually develop the equation of motion from this? Well, to apply Newton's laws, we have to work out the resultant forces and the resultant torques. All right, so how do we do this? Well, going forward, we have to decide what is the particular independent degree, or what is the independent motion in the system. For this system, we see we can swivel the rod by an angle, and then that is the displacement. They can be independently varied, and everything else will follow from that. So we have to decide what is the independent variable. Is it a direction in the x? It could be. Is it a direction in the y? It could be. Is it a direction in the angle? It could be. Why do we say that? Well, if we look at the motion of the rod will basically be in terms of arcs. So if we pivot the rod by a certain angle, it's fairly obvious that the rod will go in some arc over there in terms of that angle. So if we pivot the rod, it will move the end point of the rod by a certain direction in the horizontal direction and by a certain amount in the vertical direction. And that amount in the X and the Y direction will be dependent on how much the arc length is. And the arc length will be defined in terms of this angle. Likewise, on the other side, there'll also be an arc length, which would have a vertical component and a horizontal component. Okay, how do we relate the arc length in terms of this angle? Essentially, we'll use the fundamental formula: angle is equal to arc length over the radius. Okay, so in this case, it'll make things easier if we define everything in terms of the angle theta. We need a sign convention. We'll make our life easy. We will choose explicitly positive x in the horizontal direction, positive y in the upwards direction, and positive theta in the anti-clockwise direction. Okay, going forward, let's assume the rod is pivoting at a point, let's just call it point O, and on the left hand side and the right hand side we'll have a point A and a point B. Okay, right, how do we do this? Well, we assume it's a rigid rod, AOB, one single piece of metal or brass or whatever the case is. If it rotates in anti-clockwise direction by theta, it follows that the other angle will also be theta because it's a straight line. Alright, that's fine. What do we do from there? Okay, we assume our independent degree is theta. So theta, using our equations, theta would be the arc length SB over the radius B. Likewise, theta would be the arc length for A over the radius of A. Okay, therefore, what else do we do? What is the radius for B? This is my point where it's pivoting, and for B, it'll be the distance from here to here. That would be odd B. And for the point A, the distance would be from here to here. That would be odd A. So in this case, we would have, we assume a very small angle. So the arc length SB would be approximately this vertical distance YB. And in this case, the arc length would be roughly this vertical distance YA. So we would say the angle is the arc length, which is YB over L2, and therefore the angle would be according to our diagram. The distance from here to here is L1, and the distance from here to here is L2. Put that into our equation. We therefore have the vertical deflections of the spring and of the damper in terms of the angle and these radii. Let's rearrange the equation a little bit, and then we can solve for these deflections. Okay, so we have the vertical distance that this point B will be stretched. We have the vertical distance that the point A will be pulled down. In terms of these lengths, and the angles. Okay, so on this side we have the spring, which is being stretched by distance, and on this side we have the damper, which is being pulled by distance, which will also have a velocity. How do we work out the velocity? We just take the derivative of the displacement. So rearranging the equation, this would imply the velocity of, here we go, the velocity of B is equal to the derivative, which is the derivative of the terms that we worked out over there. L2 is a constant, theta is the variable. Take the constant outside the brackets and take the derivative of the thing inside the brackets. All right, so we've got the problem, we've got the geometry, we assumed an angle, we worked out the deflections in each of the directions, and then we worked out the velocities. Once we have the velocities and the displacements, we can then work out the forces. We'll leave it over there and we'll pick up in the next video.